Okay, so then let's start. Can you guys hear me all right?
Yeah. Perfect.
Okay, nice. So today we're going to talk about this new paper called Transformers Without Normalization. It's by Fair at Meta with Jan LeCun, among others. So this paper was discussed a lot in the last few weeks, so that's pretty much the main reason why I chose it. And yeah, let's get started. So the main idea of this paper is to show that you can take a transformer, remove the layer norm, and replace it with what they call dynamic tangent hyperbolic. So you have a layer norm and you plug in this here, which I will explain in a bit, and they basically show that this has mostly the same performance and that there are some indications that it might actually be more efficient than using the regular layer norm. So, okay, so before we go to that, let's talk little bit about normalization in like a systematic way. So there are many different kinds of normalization, right? I mean, we all know probably a layer normalization, like layer norm, which is what you have in transformers nowadays usually. And then there's also batch norm. These are all related very much, but there are some differences between them, which I will show now in like a systematic way. So all normalization layers have this kind of structure. You have here your input X, which has the shape BTC, where B is batch, T is the number of tokens, and C is the number of channels per token. So basically the embedding of the token. And then you have your mu and sigma, so your mean and your standard deviation. You have a regularization epsilon, so for the division by zero, right? Then you have a scaling and a like a offset parameter here, which have the shape C. And basically, the different normalization methods, they mainly differ in how you choose the mu or the sigma, right? So here's a little overview. This is not all methods that are in the literature. It's just the ones that are most common, and the other ones are sort of variations on these mostly. So the first one was the batch normalization from 2015. Here you average over the B and the T channels, so you get this kind of structure. And then a year later, you had the layer normalization, which is, I would say, probably the one that's used most, together with the RMS normalization in transformers, especially. And here you take your average over the C, so over the channels, right? So this is basically in this formalism how you distinguish these two. And then the root mean square normalization. The difference is basically the mean is zero, and you just take the sigma. So it's basically like the ln, just without a mean. Okay. So let's move on to the methodology. So they start out with like an investigation of normalization. This is actually something that I found really interesting and I felt was not discussed as much. This paper not only gives like a new method, really, it also gives some theoretical insights on normalization itself. So it kind of shows what normalization does in practice. So what they did here is they took different transformer architecture. So you have a visual transformer, a wave to vec, so like a speech transformer, and then a diffusion transformer. And what they did is at different layers, they looked at the normalization, like they plotted the input against the output, right? So these are just a bunch of sample points. And you can see here that in the early layers, especially, it's pretty much linear. So it's like a linear transformation. But then in the later layers, and it also depends on the type of transformer. So here for the visual, you can see it very much. This has this kind of shape, so like an S shape. And if you know what a hyperbolic tangent looks like, you can already kind of see that this very much looks like one. So basically what this means is that for small values, for small activation values, it's linear. So it's just some sort of scaling and offset, possibly. So just some linear transformation. And then for larger values in both directions, it gets pushed into a small window, right? So like very, very small, like minus 100 here gets put to minus 20. And these values get all into a small interval, basically. So it's like a squishing on the for large values and very, very small values, right? So yes, okay, I think this is
Aaron, may I ask a question?
yes, of course.
So, for example, in the second graph on top,
This one?
yeah, one input value can have two different output values, as far as I can see.
Where do
Uh,
you see this?
maybe, can I show it
Yeah,
somehow? Yeah,
no, I don't think so. But I know what you mean. You mean this, right? There's like
yeah.
this weird thing, and then there's this S shape. That's true, but you have to remember these are samples. So it might be that for some kind of tokens, it does one operation, then for other tokens, it does a different operation. So this is not You can also see that these have a spread, right? So it's not
Mm,
exactly
yeah.
a clear function,
Mhm.
but you see this kind of trend. There is a linear in the around zero, and then it gets this kind of S shape for larger values.
Okay, so for one single token, there's one single output value, but for example, one input can have like multiple tokens, so they have multiple outputs, right?
Mm,
So ln input, the ln layer normalization input, is a bunch
yeah.
of tokens, and bunch of tokens. Of course, each of them has one output, so they have different outputs. That's why there's a spread in the first graph on top, and there's kind of a strange shape in the second graph, or especially the third graph is really
Yeah,
strange.
it's not that the one individual token can give two different answers. It's just that they sampled this for a lot of data, right? So it's
Mm-hmm.
kind of messy. You get a lot of spread, and you might see some different structures. So
Mm-hmm.
there's, but you do generally see this kind of trend, right? That there is this S shape.
Yeah, yeah, I understand. What do you mean by samples? Like so.
So they just the way I imagine it, I did not look at the implementation in detail. I don't even know if they provide it, but what they basically did is just they fed a bunch of data, like depending on the kind, of course, it will be different stuff, through this transformer, and just
Mhm.
sampled what was the value before the layer normalization, what was the value after the layer normalization,
Okay,
you
okay,
know? And then they put a dot on this graph for each sample.
okay.
So you
Mm.
cannot really make like a strong statement for individual tokens based on this graph. It just shows you that there is a functional dependency that has this structure in general. There will be some other plots here. This one maybe might be interesting also for what you're asking. Okay, first I'm going to go back further. So you can see that this is a hyperbolic tangent, just to remember what it looks like. So this has exactly this kind of shape, right? If you compare like this one, for example, here, it really looks quite a lot like it, I would say.
Yeah. Yeah.
Okay, so here this is another thing they did. So if you look at the, so this is for a layer norm, right? And if you go back here, layer norm is averaged over channels. So for an individual token, this has to be a fully linear operation, right? So what this means is here they did the same plot, just now they basically everything that's from the same token, they put the same color. Okay. And so you can see here that actually for one individual token, this is linear because there goes a line through it, right? It's just for these two. These right are something else. Now, if you look at the others, you have the same. So, for example, for this yellow, it's also a linear operation. It's just that when you put all of them together, you get this S shape.
Yeah, I
Does it
understand,
make
but
sense?
what do you mean? Like, how can the same exact token has a different input location? Because it's the same exact token, right? For example, the yellow ones are the same, which
Yeah, but
green.
you get multiple values for like one token has a certain embedding, right?
Uh-huh.
And then you get different values. Like maybe one token has like 100-dimensional embedding, and then you put it through the normalization, and you get 100 values in, 100 values out.
Okay, perfect. Yeah. Okay.
And then here they did a similar
Martin,
thing, but sorry.
Martin has attended. Welcome, Martin.
Hi, Martin.
Yeah,
What's up?
can you hear me?
Yes. Should I
Okay, I thought
summarize
it
what
was
we've
later
discussed so
because
far?
Imran said it was 2 hours.
Yeah. I can wait, let me summarize what we did. So we're talking about the transformers without normalization, right? This
Okay,
paper. And the idea is to take a transformer and take out the layer normalization and put in a dynamic tangent, what they call it. Okay. So this is normalization. You get this kind of different kinds of normalization that you probably know: batch normalization, layer normalization, RMS normalization. And then we showed that they did some empirical tests where they plot the input and the output of a layer norm for different architectures, and you can see that it has a kind of S shape, which looks like a tangent,
yeah,
like a
yeah.
hyperbolic tangent. Okay. And okay, so I was just explaining here. What they did is they did the same plots, but they put for values that belong to the same token, they put the same color. And you can see that the operation for an individual token is linear because the layer norm is set averaged over the channels. So the operation will be linear for an individual token. It's not that important to understand this, but it's just a point they make. And then they do another experiment where they put values of the same channel. So for a different token, but basically different channels, like dimensions, right? You have 100-dimensional embedding, and for each dimension, you pick a different color, and then they do it like this, and you can see here that now this is no longer linear, right? You get this non-linear sort of tangent-like shape.
Okay, so so,
Okay.
so for each example, it's linear, but when you look across all instances, you have this hyperbolic tangent shape.
Yes, exactly.
But in the
So
first one, when you average the
mhm.
linears, you do still find overall the similar tangent shape, right?
Yes, because this is for different tokens, right? So you can imagine you have like one word. If we're talking about an LLM transformer, you have a word that has like 100-dimensional embedding, maybe. So you get for this token, you get 100 values in, 100 values out, and they will all be on a line, right? These 100 values. But then if you do this for a bunch of tokens and you assemble it into one graph, you still get this kind of non-linear shape overall. But for each individual token, it will be linear. That's the point they're making. Because
Okay.
I think the reason is because people will be like, what? But it's a linear transformation. How can it be have a non-linear shape? Well, this is the reason why. Okay. And then also maybe interesting point that I made, this shape will depend on the layer. So for lower layers, this will be very linear. And then for higher layers, it will become more and more nonlinear, mostly. Okay, and then just as a reminder, this is what a hyperbolic tangent looks like, a scaled one. So you get these sort of shapes that very much resemble what we saw earlier. Can you guys still hear me? I'm not hearing. I think someone muted
Oh, no.
themselves. So I cannot hear
Yeah,
you
I'm
guys
just muting
anymore.
myself because some people
Yeah,
are
yeah.
walking in the background and stuff.
It's fine. I was like, wait, did something happen? I cannot hear the noise anymore.
No,
Okay.
it's fine.
Okay. So this is what they propose now. It's called dynamic tangent hyperbolic. So it's basically just a tangent here, hyperbolic. I don't even know how do you usually say this. I always say just hyperbolic tan. I don't know how to say it with the H, whatever. This function,
I say tanh usually,
tang.
or
Oh
like
yeah, true. I also used to
10H.
say
You say
that
10H, but when you contract, it's like tanh.
10H. We put in a scaled x, so this is the input, and then again, like with the regular normalization, the gamma and beta, just as a scale and shift here, right? And then they have here some, I don't know why they really call it pseudocode, because I mean, it's pretty much just torch. So you get a c-dimensional gamma and beta, so it's the number of channels. And then alpha is just a number, so it's just a scalar. So it's literally one number. So it's less parameters than with the normalization. And so let's look at the experimental results of doing this. So I'm gonna go through so I
Go
do a bunch
to
of tests. I'm
the
gonna yeah, sorry.
can you go to the pseudocode, please?
Yes.
So, why alpha is just numbers?
I mean it's just what they chose, I think.
So they can have like different slopey S-shaped values. That's why they changed the alpha.
Mm-hmm.
Okay,
Yes.
and then you have gamma plus beta. All of them are learnable. Okay, thank you.
Yes.
Okay.
It's pretty straightforward, I would say.
Yeah.
Okay, I'm gonna go. So this is a bunch of experiments they do. They do a lot of experiments, and they all have pretty much the same results. So I will not go about them like everyone in depth. You will just see that it's sort of the same picture. So they start with a supervised vision experiment on ImageNet. So here you have the model here. So they do visual transformer and conv next in two sizes. And then you have with a layer norm and with the dynamic tangent. And you can see that the results are like the same pretty much. So there's like a 0.2% increase, but this is not really significant, I would say. It's the same pretty much. And then if you look at the loss curves, they also look very, very similar. So
What is
this
B,
one
by
here,
the way? Aaron, I missed that point. Vision transformer B. Is
I
it
think
a
it's just big and large, maybe. I'm not sure. It's the size, I'm pretty sure.
Oh,
Like
okay.
in the original VIT paper, they have like different sizes of vision transformer, right? So it's just how many parameters, I'm pretty sure.
Okay, thank
Okay. And then they do the same for self-supervised vision. So this is now masked autoencoder and then Dino. So these are two self-supervision methods. And you get, again, the same picture. The results are pretty much the same. Here, in one case, the ln was a little bit better, 0.1%, but this is honestly not significant, I think. So it's probably just some kind of randomness. For diffusion, again, they do it for diffusion transformers and look at the FID, and you get the same idea. So it's the same, right? For large language models, it's even sort of even more the same. So it's like 0.01. So they do llama, different parameters of like parameter sizes of llama they train from scratch and evaluate them on zero-shot evaluation tasks and compare it to RMS norm, because I guess llama uses RMS norm, not a layer norm. And yeah, you get the same again. And then here you can look at the loss curves.
I'm
It's
sorry.
again,
I'm really sorry. So what did they do in the benchmarks and the evaluation task for the 15 benchmarks? Yeah, for the zero shot one. Yeah.
uh, I'm not exactly sure. I didn't look at it. Just some kind of language model evaluation tasks. I don't doubt that these are like representative of the model. I mean, they get like the same value, so I think it's pretty clear that it's the same, pretty much the same model in terms of performance. But it's a good point. I have not looked at them in detail, but yeah, some kind of benchmark. Okay, Then here the loss curves, again, very similar. And then here for speech, it's the same results again. Don't think it's super. Here, okay, this is our answer. It's base, not big. So it's base and large. That's what the B stood for. Okay. And then they do one that is a little bit more interesting, or like one bit more exotic example. They do like a DNA sequence modeling task where they compared on two models that are like in the literature. I don't know either of these, but I would guess that these are like probably SOTA models. And they get exactly the same value actually. So again, it's the same in terms of this task too. Okay, so let's talk about the analysis. So just to, I think everyone got the idea. If you take layer norm, remove it, put in the dynamic tangent, it's the same. Like you literally get exactly the same results pretty much. There are some fluctuations, but I would say that probably these don't really mean much in terms of transformers. Okay, so let's talk about the analysis. So one thing they do, which is was very much discussed, which I think is also a very interesting point of the paper, they do some small scale. So this is only for the LLM. I don't know why they only do it for this. They don't really say, at least I couldn't find it. If they get similar results for other types of tasks that they look at. So for the LLM, for the llama, they look at the inference and the training time. And in both cases, so you can see here, they look at the time for the layer. So basically, how much time did this specific layer take, right? And then for the model overall. And you can see in both cases, so both for training and inference, the time for the layer was about half. So for inference, it was 2.1 seconds, and for the dynamic tangent, it was 1 second. And then for layer in training, it was 8, and then went to 5, right? And then for the model overall, it's about 8% in both cases. So, I mean, this might not sound like a lot, but I think if you're actually training a large model, you will try to get as efficient as possible. So this might actually be worth doing at the very least. But again, I want to repeat this point. These are more like initial results. They don't do a larger scale study on the efficiency. I don't know why they don't do it. To me, it sounds a little bit like they did some other tests and they didn't look as great. But that's just a guess. Maybe they just didn't do it because they wanted to focus more on other aspects of it. But yeah, this is what we have. And then, so this is a very, I think I
Can
put
I
here an
ask
explanation. Sorry?
what do they mean
Yeah.
by layer again?
So I think this is just means they just measure like in the, like how much time was spent in the computation at this specific layer. So how much time did it take to calculate all the layer norms, right? Because the whole model, you have to do attention, you have to do the MLP layer, you have to do the layer normalization, and they just measure the time of this specific layer. Because of course, you will only save time at this layer, which might be a big time save, but it also will depend on how much of the overall time of the model is actually spent at the normalization layers.
Okay,
I,
thank you.
I hope that made sense.
Yeah,
Okay.
I don't know. I don't know if I missed something, but what's the reason the reason behind it for the reduction in time or in
That's a
efficiency?
good point. Actually, I don't think they don't really talk about like what could be reasons. Might have to read again if they say anything specifically about it. But I mean, it's not that surprising, right? Because um, basically for this operation, you just have to do a tangent, and this alpha here is a scalar, right? So it's already kind of a simpler operation than doing here the whole like you have to do the square root, you have to do this subtraction, you have to do the sum here, and then you also have to multiply it with the gamma, right? So
May I ask something with the normal? Okay.
yeah,
So
sure.
the gamma and beta, why is it only
Mm.
for per channel?
Because it's like a
Okay, batch and token are the same for each dimension, but then you do it for each of the dimensions, which is channel.
yeah. So this is like how do you call this? This will like this will act on the whole BTC, but it will be the same for each batch and for each token, right?
Mhm.
This only depends on the channel, like the embedding dimension.
Mhm. So
You
why
cannot
do
you
you think,
cannot
it's kind of acting the same
what?
as an age function?
Well, you cannot do it
Like,
other way because you don't know the batch size when you design the architecture, right? And you also don't know the number of tokens
no, I get
usually,
it,
right?
but no, I'm just asking, why do you think, like to everyone, not only to Aaron, why do you think it would act like an age? Because, like, okay, they
Wait.
created
Oh, why
block.
it's oh okay. Why it's acting like 10H?
Yeah,
It's
maybe
a
we
good
can think
question.
about it. Yeah, like
So
they.
maybe I can say because I've read the paper what I think. So they don't really talk that much about like how to interpret this, but I would think that it makes kind of sense because what it's basically saying is that so the linear operation in the middle is not that exciting. I mean, it's just some linear operation, and then the S shape. Basically, what it means is that very large values you want to treat the same, right? So if you have a value that is like zero point 0.5 or like zero point 0.1, this makes really a difference, right? Because you do some operations there. But if the value is 100 or 200, it should be treated the same. It's just a large value, right? So you sort of squish these values to the to a smaller interval. I think that's basically what the operation is doing, like as an intuition.
Ah,
And the
yeah, makes
question is
sense.
yeah, why is this like a good operation to do? And I think it's just that probably this can is efficient for information processing because generally if a neuron is put just to a very large value, it does not matter like is it like 100 or 200. It's a large value. This kind of thing would be my intuition, but I
Yeah,
think
it's a
we
good
don't
point.
really know of like ultimately. Does someone else has maybe a different idea, or does it make sense to you?
I mean, it's
Okay.
not it being 0 to something positive. It's also negative, so it's not sigmoid. It should be
Yeah,
it should be
that's true.
some negative value and a positive value. So which automatically makes it kind of tan age or tunch. What did you say?
Yeah,
Tunch.
Tunch. Okay.
Yeah, it sounds less rough in French, maybe in English. It's
It sounds weird, but it's an eternal discussion what to call some math symbols. I don't know if you guys also have had this discussion on what to call maybe you, Martin, especially what to call the partial derivative d's. Like when you do a partial derivative, what to call the d, like the curly d.
wait, which one?
Like when you have
Ah,
a like df dx, and then it's a partial derivative, then you have a curly d, right? Do you know
would
what
you
I'm
say
talking
D in
about?
general? No.
Yeah, but if the like I always say del for that because I want to distinguish it from a straight up derivative that's not a partial one. Okay, it doesn't matter. This has nothing to do with this case.
Okay.
Okay. Okay, so here they do an ablation. So we just talked about the efficiency, right? Then they also do an ablation study where they basically try other functions, right? So they do. So here, this is a tanh, and then they also try a hard. I'm just going to show these. It's easier, I think. So this is a regular tanh, right? Then you have the hard tanh, which is just like a linearized version, I guess. Here it's linear, and then it's just 0 or 1. And then they also do a sigmoid. And notice the sigmoid, you can scale it, right? Because we have a scaling parameter, so you can scale it to -1, 1. It's not a problem. And then you can see that the performance of the tanh is generally the best. Here, if you use an identity, so if you don't use a non-linear function, it really like gets a lot worse. So you really need some kind of non-linearity, is what this shows. But then if you use one of the other functions, it does drop a little bit in performance, but it's pretty much the same, I would say. It's not a big difference, right? It's like a 0.4 difference here. This is a 0.3% difference. This is on the visual transformer. Yeah. So this does in a way show that tanh seems to be working the best, probably, but it's these other ones could also work, which I mean is not that surprising. You have a similar thing with activation function, right? They all sort of work, but some of them work a little bit better, probably in some cases. And I mean, if you just look at them, like especially like sigmoid, it's pretty much just looks like a scaled tanh. It's just a little bit flatter, maybe.
Yeah, it seems to me
So
the conclusion is more like everything's pretty much the same. Just use the one that's
kind
less
of, yeah.
computationally expensive.
So I mean, tanh does technically have the best results overall, so it makes sense to use it. But it's not like, wow, this really works amazingly, and all of these don't work at all. It's yeah, they are all sort of work. And then they do another ablation where they remove the alpha. So basically, you just put alpha to 1, right? And so here you can actually see again the difference is not astronomical, like not using a linear like non-linearity at all, but there is more of a difference, I would say, overall, because in all of these cases you do see like about a at least a 1% difference, which I say is significant. And it does make sense because these basically allow you to, where is it, use like choose how flat you want your tanh to be. But it is interesting that it even works sort of without the alpha. Okay.
Yeah, it makes me think maybe because you remove a parameter, so obviously I mean, you would expect to see a drop in accuracy, but it seems so minor for such a parameter.
Yeah.
It seems like overfitting to me, kind of, where you just allow the model to have to be a
Maybe.
little more expressive through this parameter that's not across the channels, remember, it's just a scalar. And so you just get a little bump in accuracy.
I see your point. Maybe they should have done some other ablation also with the other parameters to see if the alpha has a bigger impact than, for example, fixing some of the scaling or offset values. Because I think even if you fix the alpha, you can do some, in this case, in linear scaling, but you can do some scaling with the alpha to sort of cancel it out a little bit, maybe. I don't know how it will be in practice, but this would be my intuition. Okay, so this is then let me see. Yeah, this is interesting also. So this alpha, we could ask, I'm going to go back in, what is the role of this alpha value, right? And their idea basically is, which makes a lot of sense actually, this alpha should function a little bit like the sigma, right? Because it's at the same position in the normalization, sort of. Like here you do x divided by sigma. I mean, it's squared, but this is, I mean, you take the root, right? So it's of the order sigma. You do x divided by sigma. So the idea would be 1 over sigma should be about the same as alpha in practice. So what they do here is they plot for different number of epochs 1 over the standard deviation versus alpha. And you can see that actually it's true, these very much line up, especially for lower number of epochs. When you go to higher number of epochs, they separate a little bit, but still they are pretty close. And overall, I mean, you see that they behave very similarly. And then you can also see that for lower layers, the values are higher, and for higher layers, they are lower, right? So this means that the standard deviation will get bigger for larger layers, which makes sense, I would say, because they're more specialized, right? And then they do here. Wait, what was this again? Let me see. We plot the yeah, okay, this is basically a similar plot, just here they do like a scatter plot for it, right? So they just take samples of these values and put alpha on this scale and 1 over the standard deviation on this, and you can see that there is a correlation between them, right? So, yeah, basically it's the same point, right? The alpha sort of acts like the inverse of the standard deviation, which is interesting.
Yeah, I think what's interesting though is that
Mhm.
the fact that just a simple parameter can pretty well estimate the standard deviation makes me
Yeah,
think maybe something that could be tried is to go full machine learning mode, like go hard or go home, and you take all of your statistical values and you just replace them with parameters, and just hope that the model is going to learn approximately the same thing, but you just don't have to compute it. It's like
you mean
let every parameter adapt to the data, because
you
it
don't
seems like you
calculate?
can just replace it with a
Yeah,
parameter and it estimates the same value.
yeah. You're making a good point. I think probably would get probably about the same results than like doing computing the mean like actually from the data or learning it via backpropagation. Okay. Mm, yeah. So this is sort of like a standard comparison that you would do. So they compare basically their method to other alternatives to layer normalization that have been proposed. I don't know any of these. I have not looked at them in detail, so I cannot really say much about them. But they do outperform them. So yeah. I don't probably they didn't do this for all of their results because these are probably not available for all of them. So they would have had to do this themselves, which probably they didn't want to do. So you just have it for the visual transformer and for the self-supervised visual transformer. But you can see that it outperforms these especially. So I would say it makes, which yeah, it's not surprising from what we saw earlier. If it matches the LN and LN is better than these because it's the standard, so it's not very surprising.
So
Okay.
yeah, I mean, it's
Yeah,
not really.
sorry.
Uh, could you play? Okay, so I mean, it's that's really related to the kind of thing that you wanted to tell us, but I don't know, like the vision transformer B and L, are they not even like masked autoencoder from the first place? What's the difference between VITB and masked autoencoder VITB? Because I believe VITB by itself is masked autoencoder from the architecture by itself. I mean, it's not related with the kind of difference that you wanted to make from the
I
result,
think
though.
it's just how it's trained, no? Like masked autoencoder means you just have a
Yeah, we have
self-supervised method.
Yeah, I think we
So,
have
but
to map some of
yeah,
the
the architecture is the same.
yeah, some of the tokens we have to mask them in the embeddings, but I believe
Yes.
the VITP by itself is masked out in quite a while training, but I mean
Oh,
it's kind
I see I see what you mean. Um, good question.
I,
I don't know.
I'm not seeing the difference between the VITB and VITL that's masked out encoder. I believe it's already masked while it's training the VITB or the VITL from the first place. But generally, the difference in the results makes sense between the layer normalization and the DYT.
Yeah. 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 Okay.
Not really. I'm just like curious.
Yes. Okay, I think so this is like in terms of the main like results overall, this is sort of done. They also do a section on the initialization of alpha, which I'm just gonna go through rather quickly because it's a little bit more in detail. So they do some experiments on the effect of choosing different initializations for alpha, right? And basically, if you look at results for non-LLMs, it makes almost no difference. So you have to look for these you have to look at the scale. So the differences are not that big. So for example, maybe let's look at this one here. You have the conf next L and B, and then you choose different initializations for alpha, and you can see that the fluctuation is pretty small. So it's like about, how much is it actually? Like half a percent at best, which I would say is mostly noise. So there's not really a big impact of the initialization of alpha. So now the reason I showed this, you might ask, like, why? Okay, what does this mean? Because they do the same for LLMs, and for LLMs, actually, it does make a big impact. And they can show that you can find an optimal alpha 0, and that it depends on whether the normalization layer is in an attention block or if it's in another block, like an FFN block. And you can see that for the attention blocks, you will need a higher initialization, especially for the smaller models. And then for the other blocks, you will need a lower initialization, right? So I can just, they already say, see, larger models require smaller alpha 0 values. We find it's important to initialize alpha differently in attention blocks or FFN blocks, right? Okay. Then they do like another visualization of this. I don't think this is super key. They already kind of make the point here. And
Yeah.
wait, let me see. Yeah, okay, maybe it's interesting. So this is the loss, right? And you can see that for different values of alpha, you actually do get quite a gain in loss, right? So it goes from 1.935 to 1.839. So I mean, for an LLM, this is I would say quite a bit. Okay. And what was this? Yeah, so this is just basically they again show the impact for different width to depth ratios. So basically, I don't think we need to go into detail with this. The point is just that they sort of show that you can basically make a guide on how to choose the initialization for alpha depending on the size of the LLM, right? Okay. Are there any questions on this, or like, do you guys want me to talk about this more, or is it okay like this?
No, I don't think that there's anything too deep. They're just seeing
Yeah.
what values and things like this. It's like pretty hands-on work.
Yeah, I mean, I think this is not super important for the overall paper. Okay, so quick conclusion. Some points I want to make. So the first point is what I said in the beginning. So they do show sort of a theoretical result. They show that normalization acts like tangent hyperbolic. I think, sorry, this is the point I actually want to make. So if you look at the paper, just the way it's discussed online and like just read the headline or like what it's about, you might be like, okay, basically they just show, okay, I can plug this random operation layer norm, which is kind of arbitrary in itself, right? I mean, ML is all about engineering, just choosing something that works. There's not really a theory behind why it's like this, why it's not different. You just try it out, and they found out something else that works. And yeah, what's the big deal? Basically, you might ask. That also works. And I think it's a little bit more than that because they do show that what is happening in practice with the normalization is Tange like. So it's not just trial and error. You try something. There is actually an empirical intuition behind, like how would you say this? Like an empirically motivated intuition, namely, what does normalization do in practice? It does a tangent like operation, which then again motivates this paper, namely trying out, okay, how can we use this fact into designing a more efficient or simpler normalization layer, right? So this is basically how I would think about this paper. And then they show, again, you can replace the layer normalization or other layers like RMS normalization with this dynamic tangent layer, and you get the same performance, like like to the dot, pretty much the same performance over a lot of tasks. It seems to be faster, so more efficient, both in training and inference. But this, as I said, take it with a grain of salt. The results for this were not as they don't have as many results. Pretty much only for the vision transformer. So I mean, I'm pretty sure I have not looked into this. Maybe there already are more results, but we will definitely see some follow-up studies, I would guess, on this, because this paper is like already discussed a lot.
Yeah, I think
And
if I can interrupt a
yeah,
bit, I think it sort of makes sense with regards to the experiments because if
yeah,
it's like Facebook research and you're doing Llama and VIT, then you don't have much use to look at the performance gain on something else because other people will be able to take care of it and you can keep working on
yeah,
your
it's
on your
true.
stuff. So
It's just I don't know. There's maybe I'm too suspicious, but it just seems a little bit weird because this is like very much as I would say for a practitioner, this is almost the most central point of the paper. Besides, of course, from that it can reproduce the LN performance, and they pretty much only have one like what I showed. This is like the only thing they have on this question, right?
yeah, but to me this paper because it doesn't seem like what it seems like to me is okay, guys, we've been working on this on our own. It works in the use cases we have, and we're just publishing it so you guys can take a look at it for your use cases.
Maybe, yeah, yeah, you're
They're
right.
not like necessarily advocating, okay, use our new stuff. We tried it for everything. It's so good. It's like, okay, it works for us. Like you can take a look at how it works for you guys.
Yeah,
Because to me, this is the most important point. Because what they say is, okay, the usual normalization is ubiquitous. We saw that it was reproducing 10H, so we just plugged in a 10H. Okay, but if it was already reproducing 10H, then we're just doing the same thing with a different like recipe book. So what's the gain? And they say, oh, it's like a teeny tiny bit of performance, but it's less computationally expensive. And to me,
yeah.
they just said, okay, it works for us. You guys can take a look at it, or I don't know, explore some deeper reasoning later. But
Yeah, I mean, for me, I'm not this kind of. I think many people in the community are like very much super focused on just state of the art, and this they don't care about anything else. You just need the performance gain. For me, even if this was not more efficient, I would still think it's definitely interesting because it gives us some intuition about a very common type of operation. So yeah,
I think
okay.
more
Mhm.
interesting key point maybe would be why does such a shape arise? To me,
Yeah,
it
I mean,
seems like more
it's
than like a result from a physics experiment than a theory explaining it, if you see what I mean. It's like, oh, we
yeah,
saw
of
this
course,
interesting
but
result, and now it's like left to the theory
explaining
guys to
for
explain it.
explaining why this is like the basically what you would have to do is show that this is somehow an optimal solution, right, to the problem, which is minimizing some kind of learning problem, right? And I don't think we will see this in the near future because this kind of results you don't have for anything about neural networks, right?
I mean,
But I
maybe
see your
it's
point.
just specific to attention networks, not necessarily
Yeah,
any deep neural networks.
yeah. Okay, let me just finish up the rest. So this is also an important point that I did not talk about yet at all. They also do some in the appendix, some experiments for like non-transformer networks or like ResNets. And interestingly, for this, for like replacing the batch normalization in ResNets, it does not reproduce the performance. So this seems to be specific to transformers. I don't know if I don't think they do any similar empirical study like on the what the shape is for like a ResNet, for example. They don't do that. So I would guess that maybe it's just that in a transformer you have this S shape, but maybe in a different kind of architecture, like a fundamentally different, a non-transformer architecture, you get a different or like different enough shape to get so that this does not work anymore. So yeah,
This
maybe
would be
this is an
interesting
interest.
to look at the graphs for ResNet, and then maybe
Sorry.
it would be interesting to just look at the graphs or for ResNet,
Yeah, I agree. I agree.
then maybe
I
propose
mean,
something else for ResNets
yeah,
for
I mean, nobody cares because it's not
non-transformer.
transformer, but I agree. In principle, it's actually interesting to look at if it's a different shape because it sort of has to be because otherwise this would work, right?
But or
But
maybe
yeah,
something else. They look at VIT, but when you I don't remember for what experiment is it, but you showed they tried on sound data. It was like WAV something, and you had a larger difference, and it didn't test on sound on like sound transformers, stuff like this. So they use for what was the name exactly? Audio
what do you mean? So
transformers.
this is what you're talking about, right? This is for wave to vec,
No, I think
and yet
maybe it was alpha value, something like this. It was a graph.
this one.
Yeah, this one. Oh, so it's just alpha values. Okay.
Hmm. Okay. Yeah. So okay, so just the point is just that this works for transformers, but it does not seem to work for other kinds of architectures that have a normalization layer. So they don't really explain why or investigate why that is. Probably they're not really interested in it that much. It just means that this is specific to transformers, which I think is interesting and definitely has to be kept in mind. So you cannot replace every kind of normalization with this operation, which also would not really make sense because it's a very specific kind of operation, right? Okay.
Do you know what's the
Yeah.
what are people saying about this online? Because I remember you said it was kind of hype last time.
I have not done like a systematic investigation into what the
Twitter
opinion is
research
on this paper.
investigation.
I just, yeah, I've read Twitter a little bit about this paper just on the side, even before I was preparing the slides. And I've seen like a lot of people who are like very excited about, who are like just presenting, like summarizing the paper and say like, oh, it's so interesting. You can do this, right? I mean, it's interesting that you can do this. And I also saw some people who were like, probably apparently have not read the paper and said like, well, but who cares? You can replace one layer with another layer, and okay, so what? And then people said like, okay, yeah, but you get an efficiency gain. So this is what I said, right? So I think for some for practitioners, it's really the question like, okay, but does this have any? Is there like a reason to change it, or is it just like an academic question, right? Um, so I think overall the response is relatively positive, I would say. But I mean, we will see in the coming months um, how much this paper will stay on people's minds and I mean, if these efficiency results will be confirmed, then I think probably this might just become the standard thing to do for a transformer because there's no reason to do it with a regular normalization layer then because it's more efficient and you get the same performance, right?
Yeah, I think it also depends on how much you can expand it to other models or other stuff like this.
Yeah,
If
maybe.
it proves to be only very specific to
Yeah, but I mean they do a good job of showing that this that works for very different, like a lot of tasks. So this does not seem to be specific to vision or language or anything like that. It really is seems to be specific to just the transformers architecture in general, right? And if that's the case, and if it's in general also more efficient, then I think this will become uh, SOTA, sort of, right? Okay,
It
I
could
think
also
I'm
be
gonna,
interesting,
yeah.
just a thought, that maybe there's other equivalents for other architectures where you have
Yeah, I mean
some
that's what
norms.
Imran said,
Maybe it's
right?
not temps, it's like another function, and if you
You can
explore,
do
you'll
this kind
find
of
another.
analysis for every kind of normalization layer, or even other kinds of layer, I would guess, maybe, and see what happens. Probably people have already also done this kind of, but it's definitely an interesting question. Okay, anything else? Otherwise, I'm gonna end the recording. We can maybe discuss a bit more if you guys want to, but I'm just gonna end the recording here probably.
Okay, no, nothing from me. You can end it.
Okay, 1 second.